Welcome to this explainer. Today, we are diving into a fascinating and, let's be honest, slightly terrifying geological detective story. It's all about how we humans accidentally re-engineered the Earth without even realizing it. Let's kick things off with a pretty staggering number. Over 100,000. That is how many earthquakes have rocked one specific region in Western India over the past few decades. I mean, just let that sink in for a second. Over 100,000 individual seismic events in one concentrated spot. And that brings us to the central mystery of today's explainer. How on earth can the simple act of building a water reservoir appear on the surface trigger such a massive, unprecedented swarm of seismic activity deep, deep underground? Part 1, the Koyna earthquake anomaly, or a seismically stable zone no more. To kick off our investigation, we really need to take a close look at the scene of the crime, the Koyna region. Take a look at this map of the Koyna seismic zone. Notice that intense cluster of seismic activity right around those two reservoirs? Well, what makes this so wild is that this area, which sits in the Deccan Volcanic Province, was actually classified as a completely seismically stable zone until the early 1960s. It was dead quiet. And then, boom, an absolute explosion of earthquakes, all clustered right here. When you trace the timeline, the connection is just impossible to ignore. Before the 1960s, totally stable. But in 1962, the impoundment of the Koyna Reservoir begins. Almost immediately after it's filled, the ground starts shaking, eventually culminating in a massive magnitude 6.3 earthquake in December of 1967. And today, we're sitting at over 100,000 recorded quakes. The timeline is so clear-cut that scientists gave this phenomenon an official name, reservoir-triggered seismicity. Moving on to Part 2, searching for the culprit through deep drilling detective work. The reservoir is obviously our prime suspect, but to figure out the actual weapon used, scientists couldn't just look at the water on the surface. They had to drill way down beneath it. Now, early on, the running theory was that there must be a layer of porous sedimentary rock down there, acting like a giant sponge to trap the water. But deep drilling totally shattered that idea. When they drilled down, they found 933 meters of thick, solid Deccan basalt, sitting right on top of granitic metamorphic basement rock. There was absolutely zero spongy sedimentary layer down there, none. So, that leaves us with a massive question, right? If there's no porous sponge to soak it all up, how on earth is this huge body of surface water reaching staggering depths of up to 10 kilometers and triggering these deep earth tremors? Well, the answer lies in a little thing called secondary permeability. Sure, the solid basalt isn't a sponge, but it is heavily dissected by intense fracture networks. These well-developed joint sets basically act as connected pathways. Think of them as deep, watery, underground highways that funnel the reservoir water straight down into the Earth's crust. Section 3. How water triggers earthquakes, or solving the mechanics of the crime. So we've got our suspect, the reservoir, and our weapon, the fracture network. Now let's break down exactly how this actually triggers an earthquake. To really get this, we have to understand pore pressure. Imagine a heavy block sitting on a slanted slide. That block is held in place by friction, right? Now, if you inject high-pressure water underneath it, the water doesn't change how heavy the block is, but it pushes outward and upward. This reduces the effective normal stress, basically the friction that's holding the block in place. That exact mechanism is pore pressure at work inside a fault zone. Looking at this cross-section, you can literally see how the reservoir water percolates down through those fractures. It increases the fluid pressure inside the fault plains. That outward pore pressure pushes against the blocks of rock, actively fighting against the natural friction that's keeping those pre-existing faults locked together. And this directly impacts what geologists call slip tendency. It's essentially a ratio that tells us how close a fault is to the verge of failing. So as that outward pore pressure rises and the friction holding the rocks together drops, the tendency for those critically stressed faults to finally snap and slip, it absolutely skyrockets. So, stepping through the whole chain reaction, it goes exactly like this. First, rain fills the surface reservoir. Second, that water sneaks down through those deep rock fractures. Third, the pore pressure spikes at the fault zone. Fourth, the effective normal stress, that crucial friction keeping things locked, drops. And finally, step 5, snap. The pre-existing fault slips, and boom, you get an earthquake. Part 4, the reservoir water cycle and the ebb and flow plot twist. Because honestly, like any good mystery, there is a totally fascinating plot twist hiding right in the annual water cycles of these very reservoirs. When you track the data over a few years, a really stark pattern emerges. You can see the expected peaks here. High water levels correlate directly with a high frequency of earthquakes. That makes total sense based on what we just learned about downward fluid diffusion, right? But here is the twist. While peak water levels push rocks apart, you'll also notice secondary spikes in earthquakes when the water is at its absolute lowest. Why? Well, it's because the sudden drop in pressure alters the horizontal stress that keeps the fault stable. It's a phenomenon known as the depletion constant. High water triggers quakes by reducing friction, but low water triggers them by shifting those horizontal holding forces. This quote right from the research hits the nail on the head. It shows just how incredibly sensitive these underground faults are to any change in the water weight above them. Whether the reservoir is filling up or draining out, any disruption to that delicate equilibrium is going to cause the earth to shake. Section 5. Mapping future fault risks and predicting the unseen. Now that we've solved the mechanics of how this happens, how are scientists actually using this model to predict the future? Well, it translates into a remarkably powerful predictive tool. Researchers aren't just looking in the rearview mirror anymore. They're actively mapping regional fault lines and color-coding them based on their maximum slip tendency. They're essentially visualizing the invisible stress fields deep beneath the region. By analyzing those regional stress fields, they can categorize the faults. Favorably oriented faults, ones trending north-northwest to north-south, are critically stressed and basically ready to slip. Unfavorably oriented ones show a moderate slip tendency, and severely misoriented faults, trending east-west, have a very low slip tendency. This whole system allows them to pinpoint exact geographical risk zones. The big takeaway here is that by combining rock mechanics, fracture geometry, and hydrostatic gradients, scientists have successfully modeled the invisible forces beneath our feet. We can now mathematically predict which geological faults are most likely to reactivate, all based on their orientation and the fluid pressure coming from the surface. And honestly, this leads us to a pretty profound realization. Human infrastructure right here on the surface can drastically alter the stability of the Earth's crust, up to 10 kilometers underground. I mean, we took a historically stable region and threw it into total chaos, simply because human engineering fundamentally altered the deep Earth pore pressure. Which leaves us with one final provocative question to ponder about our relationship with this planet. As we continue to build bigger dams and drill even deeper into the crust, what other sleeping geological giants are we about to accidentally wake up? Thanks for joining me for this explainer, and keep questioning what lies beneath the surface.